Now let's do one example. What we have is a ideal Rankine cycle, and we know water is the working fluid. Saturated water enters the turbine at 8 megapascal. Entering the turbine, that's point number one. So we know point number one is saturated water vapor. So that's G point. And then saturated liquid exits the condenser at 0.008 megapascal, leaving the condenser, that's number three. So we know at number three, it must be F point. The net power output of the cycle is 100 megawatts. So 100 megawatts must be W cycle dot, because the unit is watts, so it must be for power. So 100 megawatts is W cycle dot. What we're looking for is first one, look for the efficiency eta. Second one, back work ratio BWR. Third one is the mass flow rate of the working fluid water in kilogram per second. Number four, heat gain in the boiler Q dot H. Number five, heat loss in the condenser Q dot C. And number six, mass flow rate of the cooling water in the condenser. Cooling water enters at 15 Celsius and leaves at 35 Celsius. We assume H is equal to HF for cooling water. Okay, so the first thing we will do is to sketch the diagram. We have a T versus S diagram. And now we sketch a vapor dome. Just like before, we sketched two constant pressure lines. Okay, let's start from number one. What is number one? Number one is the inlet of the steam turbine. The problem says saturated water enters the turbine at 8 megapascal. So number one, entering the steam turbine must be saturated vapor. So that's G point. Here is my number one. And we know the pressure of number one is given, which is 8 megapascal. Okay, and then 1 to 2, steam turbine is isentropic, so we go straight down, 1 to 2. And then 2 to 3, you cool water down. If the system loses heat, you also lose entropy. So entropy, which is the x coordinate, becomes smaller, so we move to the left. And where do we stop? The problem says saturated liquids exits the condenser. So number 3 must be F point. 2 to 3 to the left, and number 3 must be F point. Okay, 3 to 4 is the pump up the pressure. It's isentropic, so we go straight up. 3 to 4, go straight up, and then 4 to 1. That's it. That's how we sketch the diagram. And besides that, we also know the condenser is at 0.008 megapascal. So the pressure for this line is 0.008 megapascal. Okay, so now from 1 to 5, such as efficiency, BWR, mass flow rate, Q dot H, Q dot C, do you remember what is the key of solving the Rankine cycle problem? The key is to find enthalpy H of every single point. So we just need to find H1, H2, H3, and H4. As soon as we find all four of them, we're done. So let's start from H1. How do we look for H1? We start from the face. What is the face of number one? Number one is G point, so everything is pretty straightforward. Since we know the pressure, so we go to table A3. Pressure P1 from the diagram, you can see it must be equal to 8 megapascal. And the table uses bar, so we convert megapascal to bar. 1 megapascal is equal to 10 bar, so that is 80 bar. And from the table, you can easily find H1. H1 must be equal to Hg, and the value is 2758 kilojoule per kilogram. Since we're at the table, I also write down Sg, and Sg must be equal to my S1 because point 1 is point G. Sg is equal to 5.7432 kilojoule per kilogram per Kelvin. That is the unit. Okay, so we have H1 now. Next one, let's move on to H2. Again, the first step is to identify the phase. We know number 2 is within the dome, so number 2 is a mixture. If you look for enthalpy of a mixture, you have to use the weighted average equation. H2 is equal to 1 minus x2 times H2F plus x2 times H2G, and do not forget to add a subscript to the quality x. Okay, H2F, H2G can be easily found from the tables. And then the difficult one is H2. How do we look for H2? We actually have done that before. We use another property. What is the other property we use? We use entropy S. S2 is equal to 1 minus x2 times S2F plus x2 times S2G. And from here, we can rewrite this equation. X2 can be rewritten to S2 minus S2F over S2G minus S2F. Let's take a look. S2F, S2G, we can easily find those two from the table. And what about S2? Can we find S2? Let's look at the diagram. 1 to 2 is a vertical line, so they must share the same x coordinate. So S1 must be equal to S2. And do we have S1? Yes, we did find S1. So what is left is pretty straightforward. We go to the table and look for S2F, S2G, H2F, and H2G. How do we look for those? What do we know about number 2? If you take a look at the diagram, number 2 is on a constant pressure line, which is 0.008 megapascal. If we start from pressure, we go to table A3 again. We convert pressure to bar. And from the table, we look for SFSG. We call them S2F, S2G, meaning it's at pressure P2. S2F is equal to 0.5926 kilojoule per kilogram per Kelvin, and S2G is equal to 8.2287 kilojoule per kilogram per Kelvin. And then we also found H2F, H2G from the table. H2F, H2G from the table. H2F is 173.88 kilojoule per kilogram, and H2G is 2577 kilojoule per kilogram. Okay, and then I also write down nu F, even though I'm not looking for nu F at this moment. It's 1.0084 times 10 to negative 3 cubic meter per kilogram. Alright, so now I can find x2 first, and then after I find x2, I go back to this equation and find h2. Let's start from x2. We plug in the numbers. The solution for quality is 0.69. After we find quality, we can find H2 very easily. H2 is equal to the weighted average equation. We plug in the numbers. And solution to H2 is 1784 kilojoule per kilogram. So now we found H2. The next one is to look for H3. And what is H3? We actually found H3 already. Why? Because if you take a look at the diagram, how do you look for H3? Number 3 is point F, so essentially you're looking for HF at what pressure? At 0.008 megapascal. So we actually found HF at this pressure. That is just my H2F. H3 is equal to H2F. We found it already. It's 173.88 kilojoule per kilogram. So the only thing that is left is H4. H4, 324 is the pump, so number 4 is the end of the pump. How do we look for H at the end of the pump? We use one method that may be new to you. This is the first time we use it. So first of all, let's recall W dot pump over M dot is equal to H4 minus H3. This comes from first law of thermodynamics, which we proved in earlier classes. Okay, and then let's also recall W dot P over M dot can be rewritten to W dot the control volume work for process 324 over M dot. And for control volume work over mass, we have an equation for that. We proved that in the first video of this week's class is equal to integral nu dp from P3 to P4. The lower limit should be the initial pressure, in this case is P3. The upper limit should be the final pressure, and in this case is P4. WCV over M is equal to integral nu dp. We proved this equation in the first video of this week's class. So now what's going to happen is H4 minus H3 must be equal to integral nu dp from P3 to P4. Can we find H4 from here? Let's give it a try. H4 is equal to H3 plus integral P3 to P4 nu dp. Let's continue. H3 plus, what can we do about the second term in the right-hand side? Let's take a look. From 3 to 4, what is the phase of our working fluid water? You can see 3 to 4 is to the left of the vapor dome, so everything here is subcooled liquid water. So 3 to 4, the working fluid is liquid. If it is liquid, we can usually say the density must be constant. And what is my integrand? My integrand is specific volume. What is specific volume? Specific volume is the inverse of density. So if density is constant, nu must be constant. If your integrand is constant, you can pull it out. After you pull it out, you can give the subscript. You can call it either nu3 or nu4. It doesn't matter because it is constant. So which one do you think you prefer, nu3 or nu4? If we call it nu3, that's gonna be really easy for us to find the value. Why? Because nu3 is just equal to nu-f, since point 3 is point f. If we call it nu4, that will be much more difficult to find the value. So we prefer to call it nu3, since nu3 is much easier to find. And then after you pull the integrand out of it, what is left is P4 minus P3. That's it. So let's take a look. Do we have H3? Yes. Do we have P3 and P4? Yes. Do we have nu 3? What is nu 3? Nu 3 is the nu F at 0.008 megapascal at this pressure. Did we actually find it? We actually did. We went to table A3, we started from this pressure, and we found the corresponding nu F. And that is just my nu 3. So we actually found nu 3 earlier. Now we have everything. When you're plugging all those numbers, make sure you do one thing. What is that? Convert everything to SI unit. Okay, so we're plugging H3, and then nu 3, P4. What is P4? Let's take a look. Number 4 is on which line? Number 4 is on 8 megapascal line. And what is P3? P3 is on this line, 0.08 megapascal. And convert megapascal to pascal. So that's 8 times 10 to the 6. 0.008 times 10 to the 6. Mega means 10 to the 6. So finally, our solution for H4 is 181.94 times 10 to the third. The unit must be SI. It's joule per kilogram. And then we do one more step, 181.94 kilojoule per kilogram. That is the solution to H4. Now we have H1, H2, H3, and H4. Everything will be easy. The first question is to look for efficiency. The definition of efficiency, we derived the equation from last time is 1 minus H2 minus over H2 minus H3 divided by H1 minus H4. And plugging all four numbers, the solution is 0.3750. That's part 1. Very quick. Part 2, back work ratio. We derived the equation last time too. H4 minus H3 divided by H1 minus H2. So you're just plugging all four enthalpies. Solution is 8.28 times 10 to negative 3. It's very small too, so that's good. And then part 3 is to look for mass flow rate of the water. How do we look for mass flow rate? We didn't derive the equation for mass flow rate last time, but there's one given condition that we haven't used. What is that? We haven't used this one. The net power output of the cycle is 100 megawatts. And we told you earlier, this 100 megawatts must be W dot cycle. Must be W dot because the unit is watts, and watt is the unit for power. So we know W dot cycle, and we did derive an equation for W dot cycle last time. The equation was W dot cycle over M dot is equal to H1 minus H2 minus H4 minus H3. We have all four enthalpies. We also have W dot cycle. We're just looking for M dot, one equation with one unknown. We can find mass flow rate very easily. It's equal to W dot cycle divided by H1 minus H2 minus H4 minus H3. Let's plug in the numbers. Make sure you use SI unit. 100 megawatts, so times 10 to the 6 to convert megawatts to watts. And H1, 275A minus H2, 1784 minus H4, 181.94, and then plus H3, 173.88. Remember, all four of them have the unit kilojoule per kilogram. So convert kilojoule to joule by multiplying 1000. So now everything in the right hand side is in SI unit. The solution is 103.5. What is the unit to mass flow rate? It must be SI, so it's kilogram per second. This is how you find the mass flow rate of the water. And then part 4. Part 4 is also very easy, looking for heat gain in the boiler, we do have that equation Q dot H over M dot. We derive the equation is H1 minus H4. And from here, we can find Q dot H. It's M dot times H1 minus H4. We plug in the numbers. Mass flow rate is 103.5 kilogram per second SI unit. H1, 2758 times 10 to the third to convert kilojoules to joules. Minus 181.94, do it again, convert kilojoules to joules. So our solution for Q dot H is 266.6 times 10 to the 6. And the unit to our solution must be SI, which is watts. And then 10 to the 6, that is mega. So our solution is 266.6 megawatts. That is heat gain in a boiler, Q dot H. Okay, and then the next part is to look for heat loss. And we do have the equation Q dot C over M dot is equal to H2 minus H3. So Q dot C can be calculated from M dot multiplied by H2 minus H3. So now again, you just repeat plugging all the numbers. Our solution is 166.6 megawatts. So this is heat loss. And now we can double check if our solution makes sense. So heat gain is 266.6. Heat loss is 166.6. QH minus QC, what is that equal to? That is equal to W cycle. So the difference between those two numbers is 100 megawatts, and that is equal to W cycle. Is our W cycle equal to 100 megawatts? Yes, it is given as 100 megawatts, so our solution makes sense. Okay, part 6, which is the last one, looking for the mass flow rate of the cooling water. So we know 223 is a condenser. Let's sketch that. This is number 2, and this is number 3. You have the hot steam inside it. How do we actually cool it down? The way we cool it down is to let it flow through a heat exchanger. What does the heat exchanger look like? Right next to this hot steam, we put up another pipe. There's another pipe right next to the hot steam, and what's inside is the cooling water. And then the inlet, let's call it 2 prime. The outlet, let's call it 3 prime. And then what is going to happen is heat will be transferred from the hot steam to the cooling water, so that the hot steam from 223 will cool down. And then the heat exchanger itself is insulated. So the only heat transfer you have to consider is from the hot steam to the cooling water. You do not have to consider the heat transfer between the hot steam or the cooling water and the environment. Okay, so we know the mass flow rate of the hot steam from before is 103.5 kilogram per second. Now I'm looking for what is the mass flow rate of my cooling water. Let's call it coolant. What is the equation between those two pipes? We have hot steam will lose heat, so heat loss from 2 to 3 must be equal to heat gain for 2 prime to 3 prime, right? The heat transfer happens from the hot steam to the cooling water. So if the hot steam loses 1 kilowatts, cooling water will gain 100 kilowatts. Heat loss from 2 to 3 must be equal to heat gain for 2 prime to 3 prime. What is left hand side? Left hand side is Q dot 2 to 3. And right hand side is Q dot 2 prime to 3 prime. Q dot 223, Q dot 223 is equal to Q dot cold. And I have the value of q dot cold from part 5 already. So I just need to rewrite the right-hand side, q dot 2 prime to 3 prime. How do we rewrite q dot? We can refer to this format. It's equal to mass flow rate multiplied by the difference of the two enthalpies. The mass flow rate between 2 prime and 3 prime is m dot coolant multiplied by the difference of the two enthalpies. We should use the bigger one minus the smaller one. So is H2 prime bigger or is H3 prime bigger? Cooling water gains heat. So in the end, you must have more energy than in the beginning. So H3 prime must be bigger. So we use H3 prime minus H2 prime. So now we can rewrite this equation to mass flow rate of the coolant equal to Q dot C over H3 prime minus H2 prime. Q dot C is found already, so we just need to find H3 prime and H2 prime. How do we look for those? Let's take a look. The problem says cooling water enters at 15 Celsius, so that is T2 prime. Leaves at 35 Celsius, and that will be T3 prime. We also know H is equal to HF for cooling water. So what we do is we start from the temperature, for example 15 Celsius, and look for the corresponding HF, and that HF will be my H2 prime, and then repeat for H3 prime, but at 35 Celsius. If you start from temperature, you should go to table A2. T2 prime is at 15 Celsius. And from the table, you can find HF, and that will be equal to your H2 prime. The value is 62.99 kilojoule per kilogram. And then we repeat table A2 again. This time T3 prime is 35 Celsius. And from here, we can find HF from the table, and that will be our H3 prime. The value is 146.88 kilojoule per kilogram. So now I have everything I need in the right-hand side. Mass flow rate of the coolant can now be easily found. Let's plug in the numbers. Q dot C is equal to 166.6 times 10 to the 6 because we need to convert megawatts to watts, so multiply by 10 to the 6. So it becomes watt, which is SI unit. H3 prime is 146.88 times 10 to the third to convert kilojoules to joules, minus 62.99 again times 10 to the third to convert kilojoules to joules. So your solution for m dot coolant is 1.99 times 10 to the third, and it must have an SI unit. The SI unit for mass flow rate is kilogram per second. And that is this example.